So the next item is what we call cloud deployment. Traditionally, Model Center is used on your PC. So if you want to leave a job running overnight or over the weekend, you have to keep your machine on. No one else can use it. You can worry about power going down, things like that. Cloud deployment allows you to send your job to a server. It also allows you to scale massively your simulation. Again, another report from the Aberdeen group where they looked at what companies think about improving the product assessment. The first one here is use simulation earlier in the development process, and we talked about that last time. What's relevant to the cloud is two things. You have promoting collaboration between analysis experts and design engineers, and also capturing the simulation expertise from those experts and making it more accessible to others. So typically you have experts in simulation. They are different to the design engineers. The design engineers may not know about the details of how to simulate, let's say, fluid dynamics, but they know how to design wings. So what we're trying to do is make simulation more accessible. To democratize complex simulation. This is an example where we created a custom interface for a process in Model Center, and you saw the Model Center interface. So not everybody wants to learn how to use Model Center, how to build workflows. They just want to use the results. So this is an example in the oil and gas industry, and we created a web interface to do an analysis for a particular sale. And so the salespeople actually took these with them on trips and were able to work with the customers to come up with an ideal solution. In the background, they were running a complex simulation that was put together by their simulation experts. And so we achieve this through what we call cloud deployment. The players here are first modelers. These are the experts who create workflows. Once they create a workflow, they upload it to the cloud. Now, when we say cloud here, we don't necessarily mean Amazon cloud or public clouds, public computing resources. This could be something that's internal to your network and secure within your company. This could just represent your computing resources, the HPC clusters. So once the simulation is available in the cloud, then your analysts run the workflow. So these are typically the production engineers, but could also be managers, decision makers, salespeople. We found that, okay, we can provide a generic interface, and I'll show you that in a second, but most users want a custom interface developed for their process. They just want to see exactly what they need to do their job. And so we've created the tool to make that easy. And so all the different disciplines that are inside Model Center, integrate, explore, and organize are available in cloud deployment mode. Here you go. This shows you, and I'll show you in the demo in a second, the modern graphical interface, browser-based, that we've implemented for cloud deployment. I'll show you them in the demo, so I won't take time now to go into it. And here we have an example of a custom user interface, which I'll show you in a second. So again, you can make a web-based interface, or you can make a normal piece of software that will then communicate with the cloud server in the back. But before the demo, I'll show you an example that we have from JAXA. So JAXA is a Japanese equivalent of NASA and ESA. It's their space agency. We started working with them in 2008, and this group does engineering analysis for every launch of their commercial launch vehicles. One of the things they look at is to make sure that in case of a launch abort or failure, that debris doesn't fall into populated areas. So this was the simulation that they were using our tools for. Here we can see a model center model. It's multidisciplinary. There's many analyses here. We have a structural analysis, some kind of dynamic analysis, and we use SDK to predict the orbit. And this diagram here demonstrates the whole modeler analyst concept. So again, it's a little bit difficult to see here, but okay, here we have the analysts. They put together the workflows, the simulation process. They then upload it to a central server. The execution is done on the back-end clusters, computing clusters. This simulation is actually used by JAXA contractors, which were Mitsubishi Heavy Industries in this case. And they would access the simulations using the web browser and do their analysis work, and then present the results back to JAXA. The results of applying our technology was that they were able to reduce the time required to do a mission analysis by 50%. And we continue to work with them to extend the project to more users and to include more sophisticated engineering analysis. Okay. Now I'll show you what it actually looks like. So this is the front end for the cloud server. This is the default interface. So you have to have credentials to log in. And it takes you to your running jobs. Let me see if I can zoom in. You see the job name that you described. There's some additional information on it. And you can see the status, whether it's been completed or not. If it's in progress, you see the programs here. And you have some actions like you can clone a job or delete it. Another tab represents the workflows, the available workflows. So here I have you have your libraries of available processes. They're versioned, so you can go to a previous version. for example, and you can choose to launch a particular job. This takes you to a job specification screen. I'll give it a job. I specify my input parameters. Okay, this is just a simple example. I'm calculating a cube. And I submit my job. If I now go back to my running jobs, I'll see my job running, and it should complete. I can run a single job, or I can run a design of experiments. In case of a design of experiments, I have to specify which inputs I want, the range of values I want to evaluate. And which outputs I'm interested in. And once I've set up my job, I submit it. Okay, you can see the test job I ran finished. If I click on it, I get the values, and the DOE should be spooling up. So any workflow you build in Model Center normally, you can publish to the cloud, and then you can run it in this manner. And there is a default interface generated automatically. So let's look at a more complicated process. This is let's go back, sorry. Here I have an analysis for a NACA airfoil. This is a fluid dynamics analysis for an airfoil section. It's a simple case, NACA airfoil, 4 digits that define the airfoil. If I choose to launch this job, I have to specify the digits here as numbers. As a neurodynamicist, actually I want to see this airfoil. Okay, the numbers represent the geometry, but I know what a good geometry looks like. So here we've put together a custom interface to do this airfoil analysis. This is just a home window. This window here is basically to compare 2 airfoils. I'll zoom in on one, and here I can graphically specify my geometry. So these values represent the NACA digits. You can see them change here as I change this. But now I can see the geometry. So this is an example of taking a process, a workflow, and creating a custom user interface for it, using a web browser, but running the cloud services in the background. Once I'm happy with my geometries, I'm going to specify some other parameters, like the job name, the angle of attack these are running at. I've got some structural constraints, which are the front and rear spar positions, and I've got some other parameters. Once I'm happy with that, I'm going to launch the simulation here, compare airfoils. And while it's running, I can see the status of where the job is. Because in the background it's going through meshing, CFD, post-processing. If I go back to the cloud interface, I'm going to look at the jobs that are running. You can see the job that I just submitted. You can see here it's progressing now. It's creating a mesh for both runs. And now it's running CFD, which will take a little bit of time. So we haven't talked about Model Center Organize much, but this is our data management. And in the background this simulation is storing data in our data repository, what we call Model Center Organize. This is a client to let me look at the data inside. You can see here the airfoil results for different users, different dates, and different runs. As the simulation is running, I'm generating some files and saving them for later. Let me actually show you what the model center process itself looks like. See the fluid dynamics analysis, actually it was just finished there. This is the underlying model center model that we're running in the cloud. Here we specify the input variables, and we basically produce the input, which then goes to fluid dynamics. We can choose here to go inviscid or viscous, changing the fidelity of the simulation. Below is the post-processing to extract some overall characteristics. Up here, when we specify the design, we visualize the airfoil geometry with the spar positions, and once the results are ready, we see the pressure plots and the Mach distribution. So this is let's say the old classic way of running Model Center on your desktop. As I mentioned, once you want to push things off your desktop into the cloud, this is where we go to the cloud deployment. And we can see that this is still Model Center, the Model Center interface, but we created something that's meant just for the designers with the web page that you saw. So the users don't need to learn how to use Model Center. You can see here are the results. We see between the two airfoils. We see the pressure distribution. We see some summary parameters. And we can also get access to the saved files, which give us some extra information like the pressure distributions. There you go. The files that are stored here, it's hard to see, and I can't really improve the resolution, but each of the files has associated metadata. Here we store, so these are the results, and we can store the metadata saying, okay, this was generated at a particular angle of attack, particular Mach number, and these are the NACA digits corresponding here. There's also a traceability. So for some files, we include dependency links. So we can see that this file is used to generate these outputs. We can click on this one. We can see that this file was used to generate these plots. So once you generate analyses, the data goes in the system, and there's traceability stored permanently. Okay, so that's it for the cloud deployment. And now I'd like to talk about a use case that's actually still the work that's still going on, but the current results for our work with Airbus Defence and Space in Bremen.
Sorry, I have a couple of questions.
Yeah.
Sorry to chime in. So the first one is pretty easy question. So just as a curiosity, the cloud, so you are speaking about the server. I'd like to know if there are priorities in utilization of the server between the firms or government entities. So let's say NASA has a kind of priority on which kind of server. Where are placed the server? They are all in the States, UK, whatever. We have Chinese, South America, something like that. The second one, the last one, so you can answer this. This is a little bit sticky question. Why should I use this interface instead of Enhances Fluent, for example, for aerodynamics? You have a kind of comparison between the two products?
Okay. So, the first question, where things are executed. First of all, it's completely up to you. So if you have some in-house resources, your own computers, you can use them, okay? For security reasons, most of our clients won't want to do that, okay? But some of our clients, who are also commercial entities, who do have these restrictions, know that they do not want to continue to make investment into computers, okay? They want to be able to execute on Amazon Cloud, and just fire up, 10,000, maybe 100,000 computers to do their simulation. And the security issue is a well-known issue, so people are trying to address that. But the limitation eventually is that even if you have the security issue, you cannot afford to invest in computing resources. Okay, and some of the providers for high-performance computing, they are looking at security first. Okay, and they're investing a lot of effort into making it secure. So I think eventually this problem will be addressed.
So is there any kind of procedure in order to segregate? I don't know. I want to pay something more, but I want to be sure that I can operate server in North America or Western Europe.
Yep, definitely. Yeah, but even providers like Amazon will have local clusters. Some providers which are smaller but in the same business, they are certified, so you can control. Only European people are allowed on the premises, for example. So this is definitely a concern everybody is working to address. But, okay, aside from that, you can just run on your resources. The second point on using Fluent. So here we're using SU2 to run the CFD, so it's an open source code. But we could run Fluent or any other CFD tool. But we're not running it on its own, right? We're running it with the meshing beforehand and post-processing behind. If you were to manually run Fluent, you would have to somehow prepare the inputs, then take the results, and then post-process them. Okay, potentially you could do it all in Fluent, but this is what's common is a situation where you have to use different components. And so the first thing, our first offering, Integrate, is what's used here to link things together. Okay, so you have a fully automated process. So actually, you don't want to know the details of running the process or the interface of the particular tools. For example, you have a Fluent user who's familiar with Fluent, right? But let's say you, as a company, switch to CFX, right? It's a different interface. You need to learn that. So let's say you have a CFX expert who then puts this back into this workflow. The user doesn't have to change their tools, and you can build an interface that's specific not only just to fluid dynamics, but actually their design problem. Okay?
Thank you very much.
Any other questions?
Yes.
Yep.
You showed that with your tool, design a certain geometry of alfoil, you can decide the pressure distribution. Are you able to do the inverse? I give you a best pressure distribution. Can you give me best geometrical solution?
No, I know this is possible, but it's not something that our tool does. So that aerodynamic problem is solvable. I worked within Airbus, so I know they have this. Maybe not let's say with limited fidelity. Okay, but in general the problem is possible, maybe not for all solutions. But what we do, let's say you solve that problem, we can put that inside a process, link it with other components, and allow a user who doesn't know the details of doing that to use that as a black box. Okay. Anything else? Okay. So now have a look at we'll have a look at the work we're doing with Airbus Defence and Space. So this is a study for ESA, and it's still preliminary stage, but it's for a garbage collection mission. It's called the ED Orbit. The mission is to take down NVSAT, which is a huge weather prediction satellite that's no longer functioning. So right now it's not being used, and it's a liability because if something crashes into it, it will smash into many pieces and add to the debris that's already there. So like I said, it's something like 5 tons. So this is a top priority to remove from space. The question is, okay, is space debris really a problem? Here we see some damage done by space debris on the International Space Station. There's some communication with an astronaut on board, and he says he's happy that he's got quadruple glazing, 4 levels of windows. So yeah, this is happening now, and ESA is looking at the feasibility and cost of removing debris. This mission for Airbus is a way to test and qualify lots of new technologies. This is technology in guidance, navigation and control, GNC, robotics, and safety. And these technology blocks and new system architecture can then be used for a variety of applications, such as space tug, space utility vehicle, life extension, refueling, inspection, maintenance, constellation, debris removal, and finally, space exploration. Now I want to explain a little bit about what the mission actually looks like. So we have a target satellite, and we launch a much smaller satellite or a vehicle to capture it and bring it down out of orbit. So first we have the launch and the normal orbit transfer and phasing done with communication with Earth to the point where we get close to the target. At this point we rendezvous, and now we're using visual navigation with the target, and everything is automated here. So we target we approach the target, we synchronize with it, then we use the robotic arm to grab it and capture it. At this point, the arm is closed and the target actually clamps onto the, or the chaser clamps onto the target. They then enter coupled flight, and while the robotic arm is changing, there is some challenges because your whole object is changing, the dynamics are changing as the robotic arm is closing. But once the chaser clamps onto the target, they effectively become one object, which is then despun, right? The target is spinning in space. And then the chaser fires its booster to slow the whole thing down, change the orbit, hit the atmosphere, and crash down into an ocean. This is a view of this mission. So this is the chaser right now. We can see here the robotic arm folded. It's got 24 thrusters to give it maneuverability to be able to capture the target. Some visual guidance instruments. We can see here, well, the robotic arm itself. We can see here how the chaser will clamp to the target. You can also see the relative size here. Some of the instruments, and then here you can see the chaser inside the launch vehicle. Here are some possible objectives for re-entry, where they would crash down into the ocean.